So.
Oh, it's still there. Why is it still there?
If I put it back.
Exploit.o is the read thing.
Do what?
No, I didn't do that.
Yeah, it will do it if you run the .o one. Because I forgot to get rid of that. I'm going to get rid of that right now, actually. All right. All right. That should do it, right? Yeah. Which you shouldn't. Close it right now. No, I'm kidding. But anyway, so yeah. So if you want to just use that to just put your code in here and then just run it, and that will, it'll just call, or it'll run the exploit or the vulnerable program with your arguments. So do that, because that's more fun. All right. Now that I got derailed. All right. So yeah, they're everywhere. People do these all the time. That's like where like you see big serious systems that get owned. They get owned by one of these things. Or you hear somebody talk, they have like 0-day vulnerability. It's probably one of these because they're very common because programmers overlook, bounce checking all the time. And it's, just lazy, but that's all good. All right, so they work by exploiting the lack of bounce checking. We already said that. Strcpy, memcopy, and printf, which is weird because I didn't think printf could be vulnerable, but it totally is. Kind of crazy. We can talk about that later. They're all potentially vulnerable. So yeah, in order to get them to do our evil magic, we need to be a little bit clever. And that's what we're getting into. Okay, so the string copy function just takes a string and copies it byte by byte into a buffer that you give it until it hits a null byte. And it'll do this every time. And if there's not a null, even if there are more characters in the source string than there are in the destination string, it's going to keep copying until it hits a null byte in the source string, like no matter what. And even if if there's less memory in the destination string, it's just going to start writing after it. And like all the bytes from that string are going to start going into memory locations that are not part of the string. And that's where the bad things happen. All right, crazy stuff happens. Basically, yeah, like I was just saying, it just keeps going, and that's what the overflow is it'll write off the end of the buffer and just keep writing. And a lot of valuable stuff is stored after that stuff. All right, what is after the buffer? So this is a picture of the x86 stack diagram. This is what a typical stack frame looks like. Higher address that way, stack grows that way. I always get that backwards. It always there's so many different stack pictures. It's ridiculous. Okay, so basically, you have a bunch. Okay, this right here is the stack pointer. This is a frame pointer, which is what the program will use to tell where the next frame of the calling function. So every time you call a function, one of these gets pushed onto the stack. And it keeps doing that, and they'll stack up. And that's how, when you return from functions, you go back down that. So it puts all the local variables from a function right here above the frame pointer. Is that above or below? It's towards 0, but it's up. I don't know. All right. Yeah, I don't know. So this is where local variables the buffers that we're copying into, they're going to be right here. And function arguments are going to be here. They're not really that helpful because when you write to them, it goes down, and this is what we want to. This is what we're targeting here. So basically, what you're going to do is you write in characters, and when it starts writing off the end, you start overwriting all this fun stuff right here. Which this is what the program is going to use later when the function returns. It's going to use that information to help it get back to where it was. So what happens is this frame pointer gets popped off the stack, and this will get moved to wherever this says it is. and then this gets popped off the stack, and then that's where the instruction pointer will go, which is like where the program's going to start executing. So that's like prime target number one for a Stack Overflow, is you want to mess with this so that you can control where the program's going to go. Because if you can control where the program's going to go, you can do anything. So yeah, that is kind of the nature of just like a traditional Stack Overflow. Basically the same picture again. I made it bigger so you can like see it better and stuff like that. Yeah. All right. So here's a little example. We have a vulnerable function that has a local variable with 10, that it's got space for 10 characters, and then it does a copy, and it starts writing to it. So in order to hit the return address on the stack, we're going to need 10 bytes plus another 4 bytes to write over the saved frame pointer, plus another 4, and that's like that 4 is where you want to put your address. And so yeah, total like that many bytes, you know. I'm just kidding. But so yeah, by changing the return address, an attacker can divert the program flow wherever he wants. And can anybody guess where they might want to be? Like they want to make it return to? Does anybody have any sort of guess?
Their code.
Yeah, where is their code though? It's like a program. Like where are you going to write it to? You didn't write the program. You're right though. Like keep going. Yeah, there you go. You're gonna write a bunch of code in here, and when you overwrite the return address, you're gonna point it back at this thing, and so all of a sudden your program's gonna start running. You're gonna overflow the address. It's gonna jump back to the string, and it's gonna say, "Hey, I'm just gonna keep executing," and that's where your code's gonna be. And good night, Vienna. You know, like that kind of thing. So, yeah. All right. So, like I'm getting like a little bit ahead of myself, and then I'll like slide and be like, I already said that. But all right. So yeah, that's just one place though. There are several other different kinds of attacks that can be used as a buffer overflow. For example, if you have a buffer, and then underneath, like declared underneath the buffer, you have like another pointer variable. You don't even have to overflow the stack to mess with that program. You can just overflow and write over that pointer. And if someone then writes to that pointer, then your code gets written there, which is like another random place. But it works. People do it all the time, and it totally happens. For example, what you could do with that is then, so say you control the pointer, you can make it point into the global offset table, which is like a big table that a program will use to find library functions and things like that. So you could theoretically find the address of the entry in the global offset table for printf, and you can just go and overwrite the value of the code for printf. You can just overwrite it with your code, and then now next time printf is called, your code gets executed. Boom. You own it. Same basic principle with the V table is called a virtual table. It's where like pointers to virtual functions are, which no idea what a virtual function is. I just know that they exist. And so it's almost the same concept. You can overwrite pointers in the V table, and next time those virtual functions get called, boom,